Hello everyone, I'm your faculty advisor from JNFF Academy. In this video, we are going to see the solutions for the GATE Aerospace 2024 uh, solutions and the questions which have come under the concept of aerodynamics. Without any further delay, let's get into the solutions. So the first question is, yes, it's a very good conceptual question. Um, It is given in the question that there is a steady inviscid incompressible flow and the superposition of that uniform flow with a source and the flow is coming along the positive x direction. So let's try to first visualize this picture. Okay, so what is given in the question is there is a uniform flow that comes like this. So let's assume this to be capital U, and there is a source flow, and they have clearly told that the source flow is having a strength of gamma and it is situated at the origin. So maybe if this is the origin, right, and probably the source flow looks like this. Okay, so this is the source flow and the strength of the source flow is gamma. And what they are trying to say is when you superimpose these two positions, we know that we have studied in potential flow that the superimposition of these two will give you the half Rankine oval. All right, so if you the superimposition of these two will give you a flow like this, half Rankine oval like this. So basically, so this will be the stagnation point, where how the stagnation point is defined is at this point your free stream velocity, which is u, will be equal to the radial velocity of the source. So vr we call, right? Yes, source origin will be still, it will be inside. So if you see the actual picturization, it will be like this. Like this, yes, source will be still inside. So this is still source origin, and this distance, let's assume this distance to be the stagnation distance r. So now what is the question it is asked is, they are given a lot of statement regarding this flow combination, which is the potential flow combination, and we wanted to find out which is not the true statement. That's very, very important. So from this figure, it's very, very clear that option B and C are right, because in the sense which are true statements. It is located to the left of the origin. The stagnation point is located to the left of the origin. So if this is the origin and the stagnation point is this point, yes, and it is located to the left of the origin. That's right. And then it is located along the x-axis, right? Because it is on the origin, it is also located along the x-axis. As I told you how to know the distance of the stagnation point. So the location where your free stream velocity and the source velocity, radial source velocity, is equal to each other. So u is equal to Vr is nothing but we have studied in the class, right? Strength of the vortex gamma by 2 pi r. If both of them are equal, then at that point this r becomes your stagnation distance. So from here, if you derive your r, right, r is equal to gamma by 2 pi capital U. Now it's very easy to understand which statement is correct statement and wrong statement with respect to option A and D. What is option D given? The stagnation point moves closer to the origin for increasing U, which means if you increase the U, right? If you increase the U here, the stagnation point will move closer to the origin, provided the strength of the vortex is held constant. Provided the strength of the vortex is held constant. So as you increase U, your R is going to come down, right? From this equation, it's very clear. If U increases, R is going to come down because it is in the denominator. So what will happen? This distance, what we call to be stagnation distance, this will come down from the origin. So which means what? Instead of stagnation point being here, it will now, the oval will be like this. Maybe this might be your origin and this might be your stagnation point distance. It will come like that if you increase your velocity, free stream velocity, keeping your strength of the vortex constant. So that statement is right, which means that it moves closer to the origin. This statement is also right. So B, C, D are true statements. What is a false statement? Coming to option A, it moves closer to the origin for increasing gamma. That's not right, right? If you increase your gamma, which is the strength of the vortex, it will have more velocity, right? VR will have more velocity. So this will try to push even further. So if this is the origin, probably you will get a half Franken oval like this, right? Provided if you held the U constant, if you increase the gamma, the stagnation point is going to move away from origin, right? It's going to increase its distance, right, from the origin. So which is not the true statement. Then option A is not the true statement. What is asked in the question? Choose the statement which is not true. That's very, very important. Not true regarding the stagnation point location. So option A is the false statement, which is the right answer for this question. Okay. Next, this is a very straightforward question. You can get the answer just within seconds. So they asked that it's a thin aerofoil and it's a NACA 0012 aerofoil, and they have given the angle of attack. It's placed at an angle of attack of 5 degree. And what they have asked is what is the CL using the thin aerofoil theory. So we know that from thin aerofoil theory, CL is equal to 2 pi alpha, which is equal to 2 into pi into, here only you have to be slightly careful. 2 pi is in terms of radians, alpha is given in terms of degrees. So you have to convert your 5 degree into the equivalent radians. So 5 into, how do you convert it? You have to multiply this by pi by 180. So if you multiply degrees into pi by 180, then it becomes radians, because this formula 2 pi alpha, 2 pi is in terms of radians. So CL is equal to 2 into 3.14 into 5 into again 3.14 divided by 180. So CL, if you multiply this, CL will come out to be, if you round off to the 2 decimal points, 0.55 is the answer. This is a very straightforward question. Only thing, you have to take care of this conversion from degree to radians. That's it. Next. So in this question, they have given the temperature versus entropy curve for different processes. They have not given which line corresponds to which processes. There are 4 processes. Process A and A dash is one process. The line B dash and B is another process. C to C dash is another process. D to D dash is another process. So in the graph, they are given 4 different processes, and they are asking that by looking at the graph of these different processes, can you identify which line belongs to which process? Okay. So let's first go with the easy thing. B dash and A dash is more or less like a straight line with respect to parallel to x-axis and y-axis, right? So if you see B, right, it is exactly parallel to y-axis. So there is a change in temperature, but there is no change in entropy, right? Entropy is 0 from B to B dash. There is no change in entropy, only temperature has got changed. So B, if there is no change in entropy, that process is called isentropic process, right, that we have studied. If at all there is no change in entropy, the process is isentropic. Okay, then B dash is isentropic, which is very clear because there is no change in entropy. Now A dash, A dash, there is no change in temperature, but there's a huge change in entropy. You see here, from here to here, it changed. Only the entropy, there is no change in temperature. So if there is a constant temperature process, we call that process to be isothermal, right? So A dash is isothermal process. So that's also very clear. So from this, you can clearly see that either it can be, see, option A is wrong because A dash, it shows option A is not right. And again, option C is also not right, because we are very clear that B dash is isentropic, but in here it is given B dash is isobaric. So option, either it can be option B or option D. That information we can only get by solving the other two equation of lines, right? Okay, it is very straightforward. I'll tell you how to solve it. What is given in the question? the graph between entropy change and the temperature change. So let's try to equate the change in entropy for a constant pressure process, because one of them is isobaric, because the other two process they have told us one is isobaric. Isobaric means constant pressure and isochoric means constant volume. So it's very easily calculatable. What is the relationship between the entropy change and the temperatures and pressure? So we know that from the second law of thermodynamics, T ds is equal to Cp dt minus V dP. This is one of the equation for entropy change. One more equation is T ds equal to Cv with respect to specific volume dt plus P dV. If your process is isobaric, then change in pressure, this dP will become 0, right? This term will become 0. So for isobaric process, it is very easy that we can write like this. Isobaric ds by dt is equal to Cp by T, right? ds by dt is equal to Cp by T. Now because this term change in pressure is 0, and similarly for isochoric, which is your constant volume, you can take the second equation where dV is equal to 0 because change in volume is equal to 0. This can be written as ds by dt is equal to Cv by T, right? So this is a isobaric process and this is an isobaric. So we all know that ds by dt is nothing but what? If you go to the previous graph, instead of ds by dt, if you take dt by ds, it becomes the slope of all the curve, right? Because what is slope? Dy by dx. Here what is dy? Temperature. What is dx? Entropy. If you take dt by ds, it becomes the slope of each process, right? So if you just take the inverse of all these two equation, you will easily get the slope of this process, right? Say for example, dt by ds is equal to T by Cp, and here also dt by ds is equal to T by Cv. We all know for air Cp is equal to 1005 and Cv is equal to 787 something, right? So then dt by ds, Cp is in the denominator, right, which is higher value, right? So dt by ds, let's call this to be isobaric, is less than dt by ds isochoric. If it's a constant volume process, then the change in entropy, change in temperature divided by change in entropy, the slope of the curve will be higher compared to the isobaric process. Because it's very clear, right? Because 1 by Cp, it's a higher value, 1 by 1005, and here it is 1 by 787, right? So that's where. So wherever the slope is higher, then it's called isochoric process. Wherever the slope is lower, then it is called isobaric process. Now let's go to this graph to understand that. Anyway, A dash and B dash will be easily identified. Now the thing is between C dash and D dash. It's very clear that if you see by the graph, right? If you take a slope here, it's very clear that D dash has have a higher slope compared to C dash. So C dash is isobaric, where it's a constant pressure, and D dash is isochoric, right? Because it has a higher slope, which is dt by ds. So option B is the right answer. Okay. Coming to this next question, It's a very straightforward question. So they are given, consider a steady incompressible inviscid flow past two aerofoils shown in the figure. The coefficient of pressure at the leading edge of the aerofoil, the coefficient of pressure at the trailing edge of the aerofoil with finite angle is shown in the figure 1. And the figure 2 they have shown, it's a cusped aerofoil, right? Finite aerofoil means you see the trailing edge is very sharp. Cusped aerofoil is very clear that the trailing edge is kind of very curvy, it's not very sharp, it looks like this. Whereas in the finite aerofoil, it is very sharp. So by Kutta condition, we know that if we have a finite edged trailing edge aerofoil, at the location of the trailing edge, it becomes the stagnation point because you will get velocity from the top surface like this and bottom surface like this. They both will meet here, and hence the velocity will be zero at this location at the trailing edge. So for finite edge at trailing edge, your velocity is equal to 0, which acts like a stagnation point. And then for cusped aerofoil, your velocity v1 is equal to v2, but both of them are not equal to 0. Okay, so you will have v1 coming here, v2 coming from here. Both will go smoothly from here like this. That's what Kutta condition says, right? Because to make it to be one velocity here, both has to be the same velocity. So at this trailing edge, okay, at trailing edge, in case of cusped aerofoil, v1 will be equal to v2, but both of them are not equal to 0. Here it's not like that. At this location, finite edge aerofoil, v1 will be equal to v2, and at that point both will meet each other and it will become a stagnation point, and at that trailing edge it will become 0. So now coming to the CP, because question was asked at what is the value of CP at trailing edge in both the different cases of the aerofoil. When you take finite edge, CP is equal to what? The formula for is 1 minus V by V infinity the whole square. V is 0 at the trailing edge, right? In case of finite edged aerofoil, V is 0, right? Finite angle aerofoil, the V is 0. So this entire term will become 0. So CP will become 1, right? And now in case of cusped aerofoil, the same formula, V is equal to 1 minus V by V infinity the whole square. Here V is not equal to 0. It will be some value. We don't know what is that value. It will be mostly less than V infinity only, but it will be some value at the trailing edge. So 1 minus some value will come here, and then it will be always be less than 1. Correct? 1 minus some value will come here, and that value will always be less than 1. So option B is the right answer, where in case of finite angle aerofoil, CP is equal to 1, where in case of cusp, CP will be less than 1. So option B is the right answer. Okay, coming to the next question, it's a very straightforward question. What is given in the question is the aircraft was flying with a speed of V1 at an altitude where the temperature is T1 and where the temperature is T1 on day 1. So the aircraft is doing some testing. So what they have done is at day 1, maybe one day, they are testing that the velocity of the aircraft is V1. It is flying at an altitude. That altitude is T1. Okay. Maybe at day 2, the same aircraft is flying with a speed. Now it's not V1. It is root of 1.2 V1. And then temperature is also, it is flying at an altitude where the temperature is also different. Maybe it is flying at a different altitude then. 1.2 T1. So day 1 it is flying at V1 and T1. Day 2 it is flying at some other altitude. That day it is flying at a speed of 1.2 root of 1.2 V1, and the temperature at that corresponding altitude on day 2 is 1.2 T1. Now they are asking how does the Mach number M2 on day 2 compare with Mach number M1 on day 1. So relationship between Mach number, because when it's flying it might be at some speed of Mach number here, similarly some speed of Mach number here. How does the Mach number will compare, right? So it's a very straight forward question. The formula for Mach number we all know, right? What is the formula for Mach number? So as we have studied in the class, Mach number is equal to V by A, root of, right? V by A. So M1 is equal to V1 by root of gamma R T1. Similarly, M2 is equal to, instead of V2, what you have to put? What is the value of V2? Root of 1.2 V1 divided by root of gamma R. Instead of T2, it is 1.2 T2. 1.2 T1. Now if you divide these two equations, right? M1 divided by M2, V1 divided by root of gamma R T1 equal to root of gamma R T1 into root 1.2 divided by V1 into root 1.2. Everything will get cancels each other. So it becomes M1 is equal to M2. Even though it is flying at a different altitude, different speed, the Mach number during day 1 and day 2 are same. So option C is the right answer. Okay. Let's move on to the next question, which is the question that is related to dynamic and geometric similarity. This is also a very easy, straightforward question. Nothing to think too much here. Just if you know the concept, just apply, you'll get the answer. That's it. That kind of question it is. So what is given in the question? They are testing a car model on a wind tunnel where it is clearly given that the car model is 1/3. Okay, 1/3 scale model of a car is tested in a wind tunnel. So length of the prototype is equal to L, whereas length of the model is equal to L by 3, because the car is scaled down by 1 by 3, right? So length of the model is L by 3. Now since they have clearly told that it is a it's tested on the following principle of dynamic similarity. So if it's dynamic similarity, the Reynolds number of the prototype and the Reynolds number of the model has to be the same. So Reynolds number of prototype is equal to Reynolds number of model, because they have clearly given it is tested on the principle of dynamic similarity. Okay, so that way if you see, right, what is Reynolds number? Rho into Vp, velocity of the prototype, into length divided by mu, which is equal to rho into Vm, velocity of the model, into now here length is not just L, it has to be L by 3, because model length is 1 by 3rd of the prototype, right? So 1 by 3 into mu. So everything will get cancels each other, and the remaining what you have will be the relationship between model velocity is equal to 3 times of prototype velocity. Now you have the relationship between Vm and 3Vp. Now what is asked in the question, how does the drag compares? So what is the formula for drag? Drag for prototype, right? Drag for prototype is equal to of rho Vp, prototype square, into Sp, Sp is surface area, into Cm, Cd, right? So drag quotient. Similarly, drag of the model is of rho. Now instead of Vp it is Vm, Vm square, into Sm square, which is surface area of the model, into Cd. Now instead of Vp you substitute in terms of Vm, or the vice versa. Instead of Vm you substitute Vm is equal to 3Vp the whole square. Similarly Sm is nothing but sp by 3 the whole square. So what will happen? dp by dm is equal to of rho vp square into sp into cd divided by of rho. Now substitute vm in terms of vp. Vm is equal to 3 vp, right? 3 vp the whole square into substitute sm in terms of sp. So this is also square. So it is sm divided sp divided by 3 the whole square. Okay, whole square. Now if you and then put cd here, now if you cancel everything, you will get dp by dm is equal to 1. So that's the answer for this question. Okay, next question. Okay, this question little involved question. It is mathematically little involved. Concept wise is very easy. Both concepts and mathematics are involved in this question. So let's get started with this question. First, let's try to understand what is given in the question. Okay, so let me write what is given in the question. Okay, what is given in the question? So they have clearly told that the flow is flowing from the left side to the right side, and there is an elliptical object which is kept here, and because of this object is placed, there is a drag. Because of that, there is a loss in momentum. So they just asked what is the drag coefficient of this elliptical object which is placed here. They are given what is the inlet velocity profile, and they have also given what is the exit velocity profile. This loss is because of the drag that's get created, right? The momentum gets lost because of this object. That's why you see the velocity here, the velocity is uniform, right? U infinity. Here it is not uniform. At this point it is 0 and it is slowly increasing and all. And they also clearly told that line 2 and line 3 are streamlines. So it's very, the streamline started like this because of the loss in momentum of this object. Because of this object, the streamline has to expand itself, right? Ultimately the streamline should have gone like this if there is no object in place, right? It should have gone like this, right? Ultimately, if there is no object, there is no loss in momentum, the streamline which has started like this should have gone like this. Now the streamline has expanded from here to here. It expanded to some distance to accommodate the loss in mass flow, right? Because ultimately by continuity equation, your mass in m dot in, which is this region, should be same to your m dot out, which is this region, right? M dot in has to be m dot out. But we know that the velocity is getting lost because of the momentum lost. So the streamline is, or the flow or the nature is compensating by expanding the streamline to accommodating more area, because mass flow rate is rho av, right? If the velocity is coming down, and hence the streamline expands itself to accommodate more area, right? That's what is given. And because of this, what they have given is they have clearly given what is the velocity profile. Now they have asked us to figure out what is the drag coefficient, which is cd of this aerofoil. Because of that, this momentum loss has happened. So we know the formula for drag coefficient, right? But first of all, we know the formula for drag coefficient. cd is equal to d, right, 2d divided by rho u infinity square, yes, right? Because drag is equal to half rho v infinity square s cd. So now they are cd. So now we have to find out the drag and substitute it here. Now let's start with how to find out the drag. Drag finding out, it is very easy, right? By Navier-Stokes equation, we know that we already seen the similar question in the class itself. I think it's just the same question. So the drag is nothing but momentum out minus momentum in, because drag is nothing but force, right? Force is nothing but rate of change of momentum, right? Which is equal to force, which is nothing but rate of change of momentum. Rate of change of momentum is nothing but momentum out minus momentum in. So how to calculate the momentum out first? So let's put the equation now. Momentum out is equal to 0 to, see here also it is given, this is minus 0.03c to this location is 0. Okay, then this is 0 to plus 0.03c, which is called as just ht. Okay, so 0 to ht, and the velocity profile is clearly given, y by hd into u infinity. I'm just multiplying by 2 because from, see, ideally how we have to put is 0 to ht, y by ht into u infinity, then plus again minus ht to 0 into minus y by ht. But since it is a same profile, right, we can just multiply by 2 and we can make it, right? Mathematically we know that, right? If you know what is the momentum here, right, what is the momentum till here, this point, it is same in the bottom side also, right? Just I'm multiplying by 2, that's it. Okay, this is momentum out. And what is momentum? Oh, this is not just momentum out, this is into velocity, because what is the formula for momentum? U square, right? Y by ht into u infinity into dy minus what is momentum in? Momentum in is very straightforward, right? It is hu plus hu, 2hu, right? This part is hu, this part is hu, so 2hu, 2hu into u infinity square, because here you see velocity is constant, there is no change in velocity, so u infinity, just that we can add rho in both the sides, because the formula for momentum is rho will also be included, right? Yes, this is the drag that we have figured it out, right? Now if you integrate it, right, what will you get? If you integrate it, what will you get? It's very straightforward. I have done the integration by myself. If you integrate it, finally what you will get as drag is equal to rho u infinity square, because the integration is very straightforward. You see here, it is y square by ht square, so y cube by 3, right? Because here there is no integration is required, just y cube by 3. Maybe if you want I can write it here as well. Yeah, you see integral 0 to hd, this is y square by y square u infinity square by hd square, right? So y square, if you integrate it, it will become y cube by 3. Rest all is constant, u infinity square, hd square, everything is constant, rho is, everything is constant, right? And you have to do it from 0 to hd, right? The limit, if you substitute that, you will get rho u infinity square hd here. Your 2 by 3 will be there, right, in the first equation, right? You see here y cube by 3 hd, and then you will get 2 by 3 will be there because outside are 2. And next what is there? Minus this, you don't need to integrate, you can directly put it 2 rho hu into u infinity square. So 2 rho hu into u infinity square, right? Here you will also get, now here the first term is in terms of hd, the second term is in terms of hu. So you have to find the relationship between HT and HU. HT and HU is nothing but this relationship, how much it got elongated. What is the relationship between this HU and HT? For that we are using law of conservation of mass, where m dot in is equal to m dot out. So what is m dot in? Rho AV. AV is straightforward, U infinity. Here it is HU. That is what m dot in, right? Rho U infinity into HU, the distances. And it's not HU to HU, because this is HU, the another part is HU. So to HU. What is m dot out? Integral. Again, here also you can put the same thing, right? To 0 to HD y divided by HD into U infinity, rho will be there, dy. So if you integrate it, 2 rho U infinity HU is equal to y square by 2 will come, right? So obviously the 2 will get cancels each other. Y square by 2 into U infinity, and rho also we can cancel it, consider to be a constant, right? Into, and the limit is 0 to HD, right? Oh, there is a HD in the bottom as well. So ultimately you will get rho will be going out, U infinity HU equal to HD into U infinity. Here at 2 will be outside, and then you will find U infinity will get cancels each other. HU is HD by 2, which means that the relationship between the amount of the flow that got extended, right? If this length is HU, HD is 2 times of HU. Now here you can go back and substitute your drag here. 2 by 3 U infinity, instead of HU, now you can substitute in terms of HD minus 2 rho. What is HU? HU is nothing but HD by 2 U infinity square, right? Now you got your drag. Now what is CD? Drag divided by 2 drag divided by rho U infinity square area, right? Area, we know what is the area, C. Here you have to substitute C, right? Because the length of this ellipsoidal thing is C, right? C. Now we know the drag. So CD is equal to, drag has been already calculated by us. If you take the minus of all this thing too, you will get something like rho U infinity square HD divided by 3. This is drag. This is the drag component, okay? And you can put the 2 here, which is coming from the off rho divided by rho U infinity square C. And instead of HD, now we have to substitute what is the value of HD. HD is 0.03 C. So now instead of HD, you can substitute 0.03 C. If you solve it, you will get the drag to be 0.02 CD. So the drag quotient of that thin thing is 0.02. Okay, so CD is equal to 0. It's a very lengthy question. See, I have explained and solved, hence it has taken this much time. If you know this already, you can solve very quickly. Okay. Okay, this question is very straightforward, very easy question. If you know the theta beta relationship, right, for strong shock and weak shock. So there is a relationship we studied, theta beta Mach number relationship. We know that It's a complicated relationship. What we know from that equation is, for a weak shock solutions, right, as Mach number decreases, beta is nothing but your shock angle increases. That's the relationship. This is for weak shock solutions. Weak shock solutions, as Mach number decreases, beta will increases. That's what is. So what is given in this figure? They are given the same wedge. Same wedge means your theta is fixed. So nothing to play with theta here. Your theta is fixed, right? So theta beta Mach number relationship becomes beta Mach number relationship, because theta is constant here, because same wedge. So all the three cases, M1, M2, M3, the flow is supersonic. Now what they are asking is, which is having maximum Mach number, or tell us the relationship between M3, M2 and M1. But what they are given, in M3 the flow has detached, where the beta will be maximum. It's almost similar to a normal shock, right? So for M3, from the figure it is very clear that your beta is maximum, hence where M3 will be minimum for weak shocks. So M3 is the least one. So from this you see, where is M3 is the least one? From this you see, where is M3 is the least one? Option A, where you see M3 is the least one, but option D is also, you see M3 is one of the least one, right? Now the second position where your angle is more is M1, right? Here you have maximum angle, you have the second highest angle. So this will have the second highest or second least Mach number. I would say even second least Mach number. So M3 will be very low, M1 will be further higher than M3, and M2 will be having higher value. So for example, right, if you want to make you understand, M3 will be the lowest, maybe it will have, let's say, 2, and M1 will have 3, because here it's the maximum beta shock angle. Here it is slightly less than a detached one. Probably M2 will be the maximum, which is 4. So the Mach number, I'm just putting some rough examples here. M1 will be 3, M2 will be 4, and M3 will be 2. So where M3 least, M1 the next least, M3 the next one. So option A is the right answer. This is coming from the theta beta Mach number relation, but that is only applicable for weak shock. If it is a strong shock solution, it is just opposite, which is not asked in the question. Then this relationship does not hold for the strong shock, just for your information. Okay, this question is very straightforward. They have given a flat plate, and they have kept an boundary layer, and the velocity is coming like this, u infinity, and they are saying that there is a boundary layer formation like this, and they are saying at certain location L. So let's assume this is the L location. The boundary layer thickness is given to be delta, and what they are asking, what is the relationship between u and delta? So we know the boundary layer relationship is delta is equal to phi x divided by root of rex for a flat plate. So 5x divided by root of rho u L divided by mu. So if you see that, right, rho is equal to, if you take all the other terms to be like this, right, because we wanted to establish a relationship between rho and this, right, delta is inversely proportional to root u, right? So which means delta is proportional to u power minus 1 by 2, right? Rest all is not asked in the question. They are asking the relationship between, or the um, relationship between the boundary layer thickness and the free stream velocity. So it is inversely proportional to root 2. So which is answer B, delta proportional to u power minus 1 by 2. Okay, very straightforward question. Okay, this is also one of the easy question, I would say. So what they are given the question is, it's a Prandtl-Meyer expansion fan, and the inlet Mach number m1 is equal to 2 and the exit Mach number m2 is equal to 3. That is also given. So m1 is equal to 2, m2 is equal to 3. Both of them are given. Fortunately, they have also given the value of Prandtl-Meyer function as also. Nu, right? Nu of m1, which is equal to nu of 2, right? Which is also given 26.38 degrees. Similarly, nu of m2, which is nu of 3, that is also given 49.76. So that's a good news for us, right? Both of them are given. Now it's very easy that what is asked in the question is they have asked this angle, the fan angle. They asked this angle to be delta. So now let's define few more angles, right? Let's define few more angles. So you know what is mu1? The angle between the upstream Mach number and the first expansion fan, right? The first expansion fan wave, actually the first wave. So which is equal to sine inverse of 1 by m1. So mu1 is equal to sine inverse of 1 by 2, which we all know 30 degrees. Similarly, let's calculate mu2 now. Mu2 is again the angle between the m2, the direction of flow of m2, and the rearward Mach line. This is forward Mach line, right? The rearward Mach line. So basically, I would say this angle. This angle is mu2. Okay, this angle is mu2. This small angle is mu2. So mu2 is equal to sine inverse of 1 by m2. So m2 is equal to 3. So mu2 will come something close to 19.7 or something like that. You can put it in the calculator, but it is more or less coming close to 19 point something, 19.27, sorry. Yeah. Now we want to know the expansion fan, right? Angle. This angle we want to know. There it is very straightforward that first we want to know the deflection of the flow. Deflection of the flow is the x-axis angle and this m2 angle. So deflection of the flow theta is equal to mu2 minus nu1. So mu2 and mu1 we know, which is already given in the question. 49.76 minus 26.38, which will come somewhere close to 23 point something. Okay, 23 degrees point something. So the formula for delta, which is the fan angle, is mu1 plus theta minus mu2. See, that will be clearly give you the delta, right? The fan angle, which is mu1 is this angle, mu1, mu2 is this angle, mu2, and theta is this angle. So you sum these two and minus this one. That's it. That will give you the thing. So mu1 is what? 30 plus 23 something minus 19.27. If you calculate that, you will get somewhere close to 33.91 degrees. So option A is the right answer. Okay, this is very easy question, just that you have to substitute and get the answer, but nothing to think too much. It's a direct formula question. What is asked in the question is, first let's write the given information and what is asked. Okay, the given information is the mass of the aircraft, weight of mass is given. So mass of the aircraft is equal to 1000 kg, and it is in a steady level flight. V infinity is given to be 50 meter per second, and it's an elliptical plan forming, which means that the Oswald efficiency factor is 1. They are also given the span B is equal to 20 meter. They also given the S, so they given almost all the information. 31.4 meter square, which is the surface area, planform area basically, and it is flying at an altitude. That altitude density also they are given, which is 1 kilogram per meter cube, and they are given the acceleration due to gravity. Instead of taking 9.8, they asked us to take 10 meter per second square. They're asking what is the induced drag on the wing. So the formula for induced drag di is equal to half rho v infinity square s cdi. So rho is given in the question, v infinity is given in the question 50, rho is 1, s is also given, which is 31.4. Only thing CDI we don't know. We have to substitute calculate CDI, and we have to substitute in this equation. Now let's calculate CDI. CDI, induced drag, because it's not, they have not asked the drag of the wing, induced drag on the wing. So CDI is enough, not CD. CDI is equal to CL square by pi EAR. E, since it's an elliptical flank form, E is equal to 1. Aspect ratio, it's very easy to calculate. AR is equal to B square by S. From here, what is B square? B is 20. 20 square divided by what is S? 31.4. So this is what aspect ratio. What is CL? To calculate CL, they are given the information of mass. They are clearly given it is a flying, right? Steady level flight, which is means cruising. So L is equal to W. But they are given mass. So L becomes weight into acceleration due to gravity. So 1000 into 10. Because you have to get the weight of the aircraft. What they have given is mass. So mass into acceleration due to gravity. 1000 into 10, which is equal to, why are we doing this? Because we have to calculate CL. Equal to of rho is 1, V infinity square 50 square, S is also given 31.4 into CL. So if you keep this right, CL is equal to 2 into, maybe you can put 10,000 divided by 50 square into 31.4. Now you substitute the CL here. CDI is equal to 2 into 10,000 divided by 50 square into 31.4, and this is whole square, CL square, this is just CL, divided by pi EAR. Pi is 3.14. What is E1? Aspect ratio also we have figured out, 20 square into 3.14. So 20 square 3.14 will come here into 3.14. You keep this like this only, don't solve this. I'll tell you the reason for it. You see, you solve, you'll get a small value and you'll keep on wasting your time, and there is a possibility that you'll make errors. Okay, into 3.14 is very clear here, right? What is happening here? 3.14, but the surface area is 31.4. So don't keep solving it, just keep like this. Now substitute the CDI in this equation. So di is equal to half, density is 1, V infinity is 50 meter square into 31.4, and substitute the CDI here. Lot of things will get cancels each other, and finally di you will get 63.7 to one places. If you substitute this, you will get 63.7 Newton. So the answer is for this question is 63.7 Newton. Okay, cool. And the next question is, it's very conceptual question. A supersonic flow is getting into a convergent divergent duct, and the throat is here. What they're asking, what can be the velocity? Okay, which one of the following statements correctly describe the flow at the velocity? So what can be the velocity in the throat? Okay, we know that as soon as the flow is more than sonic, it is supersonic, it is coming. So obviously there will be oblique shock will be formed in this nostrils. But by the time it reaches throat, it has to be sonic. And sonic, we will get a normal shock, right? If it's supersonic, it will get a normal shock to make it to be sonic, right? So throat will always, the idea of the throat is it should have a sonic, so that it will achieve that through shock waves either in the form of oblique shock or normal shock. So by the time it reaches, it can be supersonic, so that normal shock can be formed and it will become sonic, or with this oblique shock also it can be just sonic also. So it can be either sonic or it can be supersonic. So the option A is the right answer. With this, the solution for the aerodynamics questions of 2024 is done. If you have any further questions, or if you want to get started with your aerospace career, we teach beyond gate. What is beyond next gate? Industry experts will come and teach you programmings for aerospace careers for young budding fresh engineers. Please join us with JNF Academy. Thank you.